While the coronavirus pandemic is at the forefront of our minds, it's not the only health crisis looming on the horizon. Antimicrobial resistance has been called the hidden pandemic. One of the ways to counteract resistance is by developing drugs that make current antibiotics more effective. And new research published by the University of Oxford reveals some promising candidates. Tricia Smith spoke with John Tregonning, a researcher in infectious diseases, but not affiliated with this particular study, to talk about the past, present, and future for these critical and often last resort drugs.
Antibiotics are mostly natural compounds that one bacteria makes to kill another, or one yeast makes to kill a bacteria.
I didn't know that bacteria have evolved their own antibiotics essentially in order to outcompete one another.
I guess we think of ecology as like fox eats rabbit, rabbit eats grass. Actually, on any surface, the bacteria are fighting each other for the limited resources. So the bacteria that live in our guts are trying to live off the food that we eat, and there's only a certain amount of that. So one strategy is to kill the other bacteria in the site, so you win that space.
So if bacteria are evolving to have these resistances so that they can compete with other bacteria, why is antibiotic-resistant infections, why are they becoming more of a problem?
The problem and the kind of growing health threat is these multi-drug resistance, which are called MDR bacteria, or extremely drug resistant, which are actually called XDR bacteria. And these are ones that are resistant to a whole spectrum of antibiotics, and those are the really concerning ones.
So if over time different strains of bacteria are going to evolve to be extremely resistant or have multiple resistance to antibiotics, what are we currently doing right now to counter those effects?
There has to be a sort of multiple layered approach to the stewardship of antibiotics. One approach is give less antibiotics. The second approach is to use other approaches. So we know that vaccines can protect against bacterial infections. And when you use a vaccine against a specific bacteria, you can see levels of antibiotic resistance in that bacteria dropping as well, because people aren't getting as sick, so they don't need as much treatment. And then the third thing is to develop new or enhance the quality of the antibiotics that we have.
When we're looking at enhancing the current antibiotics that we have, one of the avenues of doing that is looking at antibiotic resistance breakers. What are those?
So if we think about penicillin, when the bacteria is making more copies of its own cell wall, penicillin sneaks in and it basically makes a weaker cell wall. So when the bacteria grows, it pops. It's like putting a ladder in a pair of tights. When you stretch them, it rips open the tight completely. And that happens with the bacterial membrane. What the bacteria have evolved is something called a beta-lactamase. So penicillin as a drug class are called the beta-lactams. The bacteria have developed something called beta-lactamases, which are enzymes that can chop up penicillin. So basically, they've got a very specific pair of scissors that can chop penicillin to small bits. And so then the next kind of stage in the sort of drugs arm race is, can we develop drugs that break the beta-lactamases, that basically blunt the scissors that cut the penicillin up?
In terms of looking at these lactamase inhibitors that act as resistance-breaking drugs, what kind of research is being done at the moment into those?
So enzymes have like an active clef. The lock and key is like the most common model which people use to describe it. But basically they have a space that binds the thing that they're going to chew up. And what this group of Oxford have done is produce a compound that sits in that site and stops it being able to chew up the penicillin.
So what we're hoping is that these antibiotic resistance blockers allow us to use the current antibiotics that we have for longer. But it's not, a sure thing. Eventually these bacteria will evolve to evade those molecules that we're developing.
Exactly. This is why we have to have this kind of multi-layered approach to deal with antimicrobial resistance. If you look at the time course of when antibiotics were discovered and developed into a human clinical product, the resistance essentially emerged at almost exactly the same time. You can look at all of the different antibiotics, and the gap between antibiotic development and resistance emerging is often less than 5 years.
That's crazy that it's 5 years and then they're less helpful again.
I think some of the resistance emerged during the clinical trials. One of the biggest challenges, though, is that what you want to have is an antibiotic that you never have to use. So you develop this drug that then is never really used and there's no return on the investment. And it gets quite complicated in terms of how do we fund and develop these drugs that ideally we never use?
And we don't use them because as soon as we start using them, there's a risk that because of the exposure that bacteria will have to those antibiotics, a resistance will be developed.
Exactly. And then they're no longer your tool of last resort.